Hi, I'm Dr. Minnick, and this is going to be Lab 1 Skills for 2 EO4 2018. All right, the first piece of lab equipment you're going to need to know is a digital multimeter. So there's a couple of different ones, but they'll all say multimeter of some kind on it. They have different measurements for DC voltage, AC voltage, and then maybe resistance. And one really cool one that we're going to use right now is the short detector. So we'll turn them on with a power button there. And right now it starts off in voltage measuring mode, so there's no voltage measured between the terminals. We've got like the positive volts, there's the ground terminal, and so first thing we're going to need is some plugs. So we'll get some plugs, something like this. The other end may have an alligator clip. If it doesn't, then you can just grab a clip and attach it. So we'll put that in the red one, and we've got a black colored one to go in here. That's only to help us. So the machine doesn't know the difference between a red terminal and a black terminal. You can put in whatever one you like. It's just going to be more confusing if you don't stick to some kind of color scheme. So it's telling us, right now it's trying to measure the voltage applied between these two different probe tips, so the potential difference between there. You can see what voltage is across you, and you know, you're an electrical signal being, so maybe you'll measure something there. But what we're most interested in right now is the resistance. So let's see if we can look for shorts. So right now there's an overload. It means that there's no conduction path from one terminal to the other. You can connect them together and see that there's no resistance now. A quicker way to do this so that you don't have to keep looking back at the multimeter is to put it on the short detector mode. This has like a sound symbol, and then it'll beep when it detects a short. So this is a quick way to figure out what's connected to what, especially with something like a breadboard. All right, so this is a breadboard. This is what we're going to be using to build almost all of our circuits on this year. And the first thing to do is figure out what's connected to what. So we've got two rails that are all connected across the top. Let's just demonstrate that. So we're still in the sound mode on the multimeter there. And that's a short. That's a short. It's connected all the way across the top. And then through this wire, it's actually connected to the plug here so that you could quickly plug in a power supply or whatever you like. Now it's not automatically connected to the bottom rail there, but you could add a jumper cable if you wanted to manually connect the top and the bottom rails together. Let's just try that. So now we've connected the negative on the top to the negative at the bottom, and now we're connected all along the bottom. Okay, similarly, the positive rail at the top is connected all along horizontally, and then we've added a cable here to connect it to the plug. You don't have to do that. That just makes it a little bit easier to connect to things like power supplies, like we're going to do later. Now these rails on the top are not automatically connected to any of the plugs in the middle here. Now these plugs in the middle work differently. These are all connected vertically. So if we were to put a connector there, then we're not connected left and right, but we are connected up and down. And across the jump in the middle, it's not connected either. So every port in the middle, along the top or the bottom, is just connected vertically. So specifically, the question that we're going to do today is this one. Here's a sample lab test number 1. So the question is to analytically solve for the voltage at nodes A and B. So that's A and B there. And the current through R3 and R4, and show all your work. Then simulate it in multisim and measure those same things. And then build a circuit on a breadboard and measure the voltages at nodes A and B and the currents through R3 and R4. So do the same thing 3 different ways, the 3-phase testing approach, and we've got the analytical solving, multisim, and the circuit building and measuring. So here's the result of doing analytic solving. So there's other videos on this that should be going up on the channel soon if they're not there. Here's a mesh analysis solution. We've got VA is 1.58, VB is 0.09, and IR3 is 1.95 milliamp. IR4 is 21.95 milliamps. We can do the same kind of a test with multisim. So the multisim video should also be up, hopefully. And we can just verify 1.58, so the same kind of voltage that we got there, and 91 millivolts, so 0.091, really small font, and also the current with the ammeter measurement. So 20 milliamp going the other way, and we can move that down there. In R3, we should expect 1.95 milliamps in the down direction, and through R4, we should expect 22 milliamps going to the right. Same as we found analytically. So now we're on a good start here. We have pretty good confidence that the multisim and the analytic are probably both right since they agree with each other, but we have to double check by building the circuit live. Okay, so we're going to need some resistors and we're going to need 2 power supplies. So let's talk about the power supplies. Power supplies we have in the lab are just labeled power supply. There's 2 different kinds here. So we've got this power supply and we've got this power supply. Because right now it's measuring the voltage, it's reporting the voltage. This style you can push in a button to see how much current is being delivered. Right now it's 0 and that's because the output isn't connected to anything. And you can adjust the voltage limit and the current limit with these 2 different knobs in the front here. So this is a coarse adjustment, this will adjust it a lot, and a fine adjustment which will adjust it a little bit. So you want to use the coarse adjustment to get roughly in the right range, and then the fine adjustment to get into exactly the right value that you need. Now this doesn't have a lot of decimals of precision, so it's a good idea to double check what you're reporting on the front of this terminal using a multimeter. Which power supply is our voltage supply and which one's the current supply is up to you. You could make either one the voltage supply or the current supply. You'll notice that these are both power supplies rather than like current or voltage. What makes it a voltage supply is placing voltage as the limiting factor. So that means you would have the volts to say 2.5, and you would double check that it has enough current to be able to supply that. So if while the circuit is operating you find the voltage is dropping below 2.5, you need to increase the current limit. If you find that you're increasing the current limit too much above 0, then there's probably something wrong with your circuit. It is possible with this lab, definitely with the power supplies involved, to put too much current through the resistors, which is going to heat them up, and then they're going to burn and feel really hot when you're touching them. You can easily burn yourself. So definitely be careful not to put too much current through the resistors. Okay, let's see how to measure what's going on with this supply. So very important, we want to take this off of the short measuring mode and switch to DC volts. Then we can use our probes from the multimeter here to measure the voltage that's actually being supplied by the power supply here. So it's reading 2.5. Multimeter says it's about 2.59 actually. So we want to adjust the voltage that it's supplied until the multimeter gives us a close enough value so that we're happy. And wow, that's pretty good. So you don't have to get 4 or 5 decimals of precision with your value. If you're feeling really lucky, then you can try and go for that. But you know, anywhere within 1 or 2% is totally fine for the labs that we're going to do. Okay, so rather than complicate things at first, let's try and build just the left-hand side of this circuit. So we've got our 2.5 volt supply, and we're going to need to connect this up to our breadboard somehow. So let's turn it off while we're doing that, and take the connections from this supply. Since we've gone and wired the top plug to the red rail and the top black plug to the negative rail, positive and negative, we can just connect up the power supply like that, and we're going to have 2.5 volts placed across these rails. So turning the power supply back on, it stayed at 2.5 volts. We can now take our multimeter, put back the alligator clips, and confirm that we have 2.5 volts across that top rail. Yep. So now that's on the breadboard, and we can use jumper wires to get that to the resistors that we need. So before we do that, we're going to need to actually get those resistors. Now it looks like we need a 100 ohm and a 220 ohm. Now, if everything goes well, then for you, this is all going to be in these containers over here, which will be labeled as well. Still, you can't be 100% sure that the student before you hasn't put something back in the wrong container, so you have to double check what the actual value of the resistor that you're using is. Always a good practice. So let's get ready to do some resistance measurement here. We're not going to need the power supply for now, and we'll go over to our resistors, which right now are in this container here. So we have 100 ohm, should be in this box here. If you learn how to read the bands on them, then you may be able to recognize 100 ohm if you're a superstar. You can always double check by reading it using the multimeter. So we've got 96.26 ohms. So that is 100 within the tolerance of both the multimeter and also of the resistor itself. So these resistors are what they're labeled plus or minus 5%. So that means we're going to say that for that one we actually used a 96.3 in case we want to double check our work later. And in the circuit we're going to need to connect the top of the power supply to this one. So on the breadboard what we'll do is we'll take the red rail, which was the positive, and we'll connect it over, let's say, just into this port there. Then we're going to find our 220 ohm and connect from there to ground to build the other part of the circuit. So let's look for that over in the resistors here. 220 should be in this little compartment. Let's double check. So that doesn't look right, does it? This is definitely not 220 ohm. This resistor in particular is a 1.2K. So that's no good. This was put back in the wrong container. So 1.2K should actually be here in the bottom compartment. Prime example of why you should double check the resistor values before you use them. Let's see if we're lucky with another one of these supposedly 220 ohm resistors. When we're doing this measurement, it's important not to hold the terminals with your hands, because then you're going to be simultaneously measuring your resistance in parallel with the resistor. For high values of resistance, so on the order of hundreds of kilo ohms, depending on what your skin conditions are, that can affect the measurement. So this resistor is, as advertised, around 220 ohm. So in particular, we've got 217, good to keep track of for later in case we want to double check. And we want to place this from the other side of the 100 ohm resistor to ground. So we can do that by jumping in beside it on the breadboard vertically, and then connecting from there to our ground, or the other side of the power supply, which we've connected to this terminal there. Okay, so now if we turn on our power supply, notice that we can have the current turned pretty far down without it reducing the voltage. That's a good sign. This voltage for these resistance values, you can do a quick calculation, around 320 ohms, 2.5 volts. We should expect less than 10 milliamps going through. So a pretty small current going through. If you found that the voltage was getting shut down too much by the current limit, then that probably means there's some kind of a mistake, maybe a short somewhere on the circuit. So now we're in a good position to measure the voltage while this is operating and double check that things make sense. So we'll get our probe wires out again. And we can measure voltage from negative to positive. Double checking, we still have 2.5 volts as reported by the power supply. And we can measure the voltage divider across the two resistors. So this is measuring, now I've placed the positive terminal at the other side of the 220 ohm. So we should have 217 divided by 217 plus 96 times 2.5. If we do a calculation, so 2.5 times 217 over 96.3 plus 217, we get 1.73, which is exactly what we get in the multimeter. Okay, so next thing we're going to need in the circuit is the current supply. So to get the current supply working, we're going to need to learn how to measure current in the lab. In principle, these digital multimeters can also measure current. So we've got DC 20 amp, AC 20 amp. You would use the DC 20 amp to measure the current. Now current goes for a different positive terminal. So we've got a maximum 2 amp and a maximum 20 amp over here. However, these circuits are all not going to work if you do this, and that's because these multimeters don't have fuses. So the AC measure, not AC, but the current measurement on the multimeters is not going to work. So if we had a fuse in here, then you'd be able to use this to measure current, but we don't. So because all the fuses are gone from the digital multimeters, to measure current, we are going to use a more archaic piece of technology called an analog multimeter. So here is the analog multimeter. Just to double check, we've got the current turned way down, and now we can apply the current that we'd like for this. So we've got 3 different inputs here. We've got a ground, we've got volts, amps, and ohms, and we've got a 30 amp. So this is the high current range. So let's first make sure that we are on one of the current ranges, so here milliamps and amps, and then we will apply ground there and the positive terminal up there. And now, looking back at the power supply, you can see it's dropped to a very small amount. So rather than the 2.5 volts we had before, it's down to only 0.5, and that's because the current is now limiting things. So if we start to turn up the current here, then we'll rise until we end up with a voltage limited value. Now, you'll find that as we move this around, the current isn't increasing on the supply here, and we're also not measuring anything on the multimeter, and that's because you definitely have to make sure that the multimeter is set up correctly. So there's a couple of things that are important about this. First of all, we're on AC mode. We definitely want to put it on DC mode in order to be able to measure the current correctly. Next thing is we're on negative mode. So this is trying to measure negative current going in the other direction. We could switch around the probe terminals and see it go all the way to full scale there, or we could just switch it to positive mode and now it'll measure in the other direction. So right now we're at full scale. We need to increase that so there's more than 0.3 milliamps, definitely, more than 1.2, more than 3, 12, 60. And on the 12 range, we can start to see the current supplied. So this is a 12 milliamp range. Now, at the top here, you would read either the very top set of numbers, where it goes full scale from 0 to 120, or the set of numbers below that, where it goes 0 to 30 or 0 to 60, depending on what range you're on. So for a 12 range, it's 120 is the full scale. So right now we're on a range which is labeled 12 milliamps, and if 120 full scale would correspond to 12 milliamps, then 95 would correspond to 9.5 milliamps is the amount of current that we have going out right now. So we need to set up a current supply so that we have 0.02 amps, which means we're going to want 20 milliamps. So how we would do that is we need to put the multimeter here on a scale that can measure up to 20 milliamps, so the 60 milliamp range here. And that means we're looking at the scale that goes 0 to 60, and we need to increase the current limit until we get this to be a reading of 20. And there we go. Now it's set up as a 20 milliamp power supply. So we did this with the power supply on the left. We can do the exact same thing with the power supply on the right. So first thing to do is to make sure the current is turned all the way down. So that's turning counterclockwise to bring things pretty far down. We'll put the voltage at some small amount for now, and try the same thing with this power supply. So this power supply looks like it's not going to work because we're saturating full scale even with the knobs turned all the way to the left. So because of that, you may have to be careful about which power supply you select to be your current source and which one you select to be your voltage source. Power supply here is too sensitive to current in this really low range, so we better make the other power supply the current source, which means we're going to need this one to be our voltage source. This one's still supplying 20 milliamps, and now we can set up the other one as a voltage source, just like we did at the beginning. We could also use the analog multimeter to measure voltage if we like to, but since the digital multimeter is there and ready to go, let's just hook it up for that. Getting to 2.5. Great. Okay, so now we have our 20 milliamp current source and our 2.5 volt voltage source. Next part is to get the other resistors and then hook them up in the circuit. Okay, so let's bring it to a close then. So we've got our new voltage supply over here, and we can hook that up to the circuit by plugging back in, and this gets everything to the way that it was before. We'll see if the voltage drops. Not really. Looks like it stayed about the same. Let's double check that everything is still working. So about 2.5 across the different terminals of the circuit, and we can measure the voltage divider and see if that's still about 1.73. Looks good. Everything seems like it hasn't broken by switching to the different supplies, so that's great. Next, what we're going to do is get the other resistors that we need for this design. So in this case, that's a 47 ohm and a 68 ohm. So, being sure to measure the resistance values, get our probes back for the digital multimeter, place the digital multimeter back in resistance measuring mode. Very important not to try to resistance measure while the circuit is actually going, or your results won't work. So in this container, 47 and 68 should be along the top. So let's see if we can get a 47 here. Looks good. 46.7. And this is connected on one side to the ground, and on the other side we're going to need to connect it to the current source and then to the voltage divider top that we were playing with over here. So let's put this anywhere on the breadboard where we're going to have space to connect it to the current source. Okay, now the other resistor we need is a 68 ohm, so we'll go back over, grab from the 68 container, and then double check the resistance of this. Multimeter says 67.3. And this one is going to end up in parallel with the current source. So that means one end of it is going to be connected to the top of the 47, and the other end is going to be connected to the voltage divider network. So there's connecting the 68 to the top of the 47 and other end to the voltage divider network. Now what we need to do is put the current source in parallel with that. Current source right now is connected up to the ammeter here. So what we can do is get additional alligator clips, and important to find some way to not have the wires short out anywhere or connect anywhere that they're not supposed to. So now we've connected the current supply in parallel, but which way should it be going? So let's just double check. Looking back at the diagram, we need the negative terminal of the current source to be at the top of the 47. So that's actually hooked up like this with the negative, and we'll need the positive of it hooked up on the other side. Okay, so the last thing to do, we've got all the resistors in there, and we've got the voltage supply, which is now switched to the new supply. We just need to add in the current supply. So current supply is this machine here again. We've got the negative terminal. The negative terminal of the current supply should be this side, and so we're going to connect up to that on the top of the 47 ohm resistor there. Then we'll take the positive side of it, and just for now, let's keep the ammeter in the picture. So we'll put the positive side of it into one side of the ammeter, and take the other side of the ammeter and put that at the other side of where the current supply should be connected. So that's where our voltage divider was before. Everything looks good, still limiting to around 20 milliamps. And now let's check the different voltages. So in our calculations originally, we had with multisim that we expected we expected 1.58 volts for node A, and node B we expected 91 millivolts. So let's check what we actually get. Node A, we've got our multimeter in DC volts. We're measuring relative to the ground, and at node A we get 1.62 versus the 1.58, so that's pretty close. Now at node B we measure 0.07 as opposed to 0.09. So that one looks a little bit further off from a percentage standpoint, and it actually has to do with the sensitivity of this particular circuit to the current supply, the current that's actually supplied. So if we go back over here into our analytical calculation and we substitute in the actual resistors that we measured and we run things again, we see that VB is a little bit different than we first calculated, just about 10% off. It's actually 10% in the other direction compared to our measurement in the lab. But if we increase the current from 20 milliamps to 23, now VB drops to 0.047. And it's kind of tricky to measure to within a couple of milliamps using the analog multimeter exactly what current we're supplying. So then if this analysis is right, it means the current might be a little bit too high for what we're supplying to get the measurement that we're looking for. So if we want to turn this to 0.99, we can make a little bit of an adjustment here and see how sensitive that is. It changes the voltage that's applied quite a lot. So this one, we've gotten this result, wow, to be pretty much exactly what we calculated, and according to the ammeter, that happens when we've got around 18.5, 19 milliamps. So there you have it. Thanks for watching. I'll see you next time.